Okay, let's move on with our exploration of linear independence. We're now going to relate linear independence to the notion of span. Recall that the span of a set of vectors is the set of all linear combinations. Okay, so we have this lemma. Suppose that S is linearly independent and you have a vector that's not in S. Then the set S union V is linearly independent if and only if V is not in the span of S. Okay. And I think that before proving this, let me try to give some intuition here. Let's take a linearly independent set. We know that 1, 0, 0, 1 is linearly independent. We already proved that. Okay. Now, V is another vector that's not in S. I could take the vector V in the same plane, defined by these two vectors. All right. You could show, in this case, that these three vectors are not linearly independent. Okay. But also we can see that this vector is in the span of these two because I can scale this one up slightly to here, and I can scale this one up slightly to here. And the sum of this vector here plus this vector here gives me this vector here. If I use the head-to-tail rule, sum of this vector here plus this vector here, which is the same thing as this vector here, gives me the vector V. So let me clarify this a little bit. This would be S1 here. This would be S2. And this would be V. And in this case, V is in the span of S. And S1, S2, V is not linearly independent. Okay? That illustrates one way of this if and only if. We've shown that if V is in S, then these three vectors are not linearly independent. That's the contrapositive of S1, S2, V, linearly independent, implies V is not in the span of S. So this example here is an example of the contrapositive of this statement here. Now remember, when we try to prove something, we can prove either the statement or its contrapositive. So you should try to understand that those two are equivalent. All right. So this example illustrates this statement here, which is 1/2 of the lemma that we want. All right. Now on the other hand, if I have S1, if I have S1 pointing this way, and I have S2 pointing this way. By the way, I emphasize that this is not a proof, this is just an example. This is just an example. Okay, so this is an example of this statement, which is 1/2 of the statement we want to prove. On the other hand, if we take S1, S2, and if we take V out of the paper, in other words, V is not in the plane determined by S1 and S2. Well, there's no way to take a combination of S1, S2, and V that will give 0, unless you take all the coefficients equal to 0. Okay? So in this case, there's no linear relation for S1, S2, and V. And what does that mean? No linear relation is the same thing as saying they're linearly independent. Okay. Now, if I take V out of the paper, that's the same thing as saying V is not in the span of S. Okay. So what we've shown here is an example of the other direction of the lemma, that if V is not in S, then the set S with V added is linearly independent. Okay, so think about these two examples. These two examples illustrate this lemma. So another way of summarizing this is that if I have a set of vectors and I want to essentially add to the span, I need to add a vector that's not already in the span. And on the other hand, if I add a vector that's already in the span, I won't add to the span of the result. Okay. So let's see. So we will show that S union V is not linearly independent if and only if V is in S. All right, now notice that this statement here is logically equivalent to this one. We have implication two ways here. The statements here are the contrapositives of the statements here. So they're logically equivalent. Now remember, not linearly independent means that there is a linear relation among the vectors. Okay. All right, so let's first show that V is in S implies that S union V is not linearly independent. That's showing the, if you think of if and only if as a two-way arrow, that's showing the arrow in the reverse direction. We're showing V is in S implies that S union V is not linearly independent. Okay? And this just involves writing down what all of these things mean. Okay, first of all, suppose that V is in the span of S. That means V can be expressed as a linear combination of the vectors in S. We can rewrite this by putting V on the right-hand side. That means there's a linear relationship among these vectors, which are in S union V. And that means that S union V is not linearly independent. Okay, so that shows the negative implication. Now we'll show the positive implication that S union V is not linearly independent, implies that V is in S. Okay. All right, suppose that S union V is not linearly independent. That means there must be some kind of relationship among the vectors in S union V. Okay. Now, in fact, in this linear relationship, C n plus 1, which is the coefficient of V, cannot possibly be 0. Because if it was 0, then we'd have a linear relationship among the S's, but we know that S is linearly independent. Okay, so we know that this coefficient here is not 0. We can conclude that the coefficient is not 0. Since the coefficient is not 0, we can write V as a linear combination of the S's, which means that V is in the span of S. Okay. So there are some things that you need to probably need to look over this again. Instead of proving the implications directly, we proved the contrapositives, and we proved the contrapositives just by directly using the definitions. All right, here's an example. Let's consider in polynomials of degree less than or equal to 2, we consider these two polynomials. These are linear polynomials, so they certainly have degree less than or equal to 2. The span of this set of two vectors is the subset of all linear polynomials. You can check that you can get any linear polynomial as a linear combination of these two vectors. For example, if I take 1 minus x plus 1 plus x, I get the polynomial constant 2. If I take 1 minus x minus 1 plus x, I get the polynomial minus 2x. So I can get any polynomial a plus bx as a combination of these two polynomials. Right? All right, and you can prove that mathematically. To see the span as the set of all linear polynomials, consider a linear polynomial a plus bx. then I write a plus bx as a linear combination of these two polynomials. And I can solve for the coefficients r in such a way that a plus bx is a linear combination of these two linear polynomials. Okay. Now suppose we add this linear polynomial, 2 plus 2x, to the set. Now really I have not increased the span because I already can express 2 plus 2x as a linear combination of these two polynomials. Okay. So I haven't added anything to the span. The span of S1 is the same as the span of S. On the other hand, if I add a quadratic polynomial to S, then certainly 2 plus x squared is not a linear combination of these two polynomials. And in fact, the span of S union 2 plus x squared is all of the second degree polynomials. And we can show this in the usual way. Write an arbitrary second degree polynomial as a linear combination of these three given polynomials, and you can solve for the three coefficients. Okay. All right, so the span of S2 is all of P2. Okay, so corollary, in a vector space, any finite set has a linearly independent subset with the same span. The idea here is that if you have a set of vectors, you can just keep on throwing out vectors that are linearly dependent until you get a linearly independent set, and you haven't reduced the span. Okay, so let's see how that works. Well, first of all, let me show you an example of that. Suppose I have three linearly dependent vectors. I can be even more fancy. Suppose I have four linearly dependent vectors like this. Okay, these vectors are all in the plane, and they can be added. You can find a non-trivial linear combination to give 0. For instance, this vector plus a multiple of this vector minus this vector gives me 0. Okay, so these are linearly dependent. Okay, suppose I throw out this one. Okay, now these are still linearly dependent. Okay, suppose I throw out this one. These are linearly independent. Is the span of these two any smaller than the original span? The answer is no. And why is that? Because the two vectors I threw out are both in the span of the two vectors that I kept. Okay, so that's what we're talking about here. You can always remove redundant vectors and reduce your set of vectors to a lean set of linearly independent vectors. Okay. All right, so first of all, let's take an arbitrary finite set of vectors. Now, if that finite set is linearly independent, then S already satisfies the statement. Okay. So we need to consider the case where this set is linearly dependent. We want to cover all the cases. We've covered the case where it's independent, so now we need to cover the case where it's dependent. Okay. By definition of dependent, this set S contains a vector V1 that is a linear combination of the others. So I define S1 as this set S with V1 removed. Okay. By corollary 1,3, the span does not shrink. Okay, remember corollary 1,3 back here. Okay. If I throw out a vector, it's not going to shrink the span. Okay. So I threw out a vector, it doesn't shrink the span. Okay. Let's see, where am I? Oh, sorry, I'm already here. Okay. Okay. If S1 is linearly independent, then we're done. Otherwise, we throw out another vector. Okay. And we can get an even smaller set. And each time we throw out the vector, we don't change the span. Okay. Eventually, we have to get to a linearly independent set. We can't throw out all the vectors because then that will reduce the span. So we just keep on throwing them out until we finally get to a linearly independent set. Okay. So again, any finite set of vectors, you can always extract a linearly independent subset. Okay, so consider this example. Okay, this is a good example. So here we have 1, 2, 3, 4, 5 vectors in the plane. Now if we try to form a linear relationship among these 5 vectors, we get a system of 2 homogeneous equations. We can do row reduction, and we can express the solution for these coefficients as a arbitrary linear combination of 3 vectors. Now suppose I set R5 equals 1, R2 equals R4 equals 0, and that gives me solutions for R1 and R3. And that shows that S5 is in the spin of S1, S3. Okay. On the other hand, you can show similarly that S4 and S2 are in the spin of S1, S3. So I could throw out S2, S4, and S5 and keep the same span. Okay. However, S1, S3 is linearly independent, and we can't throw out any more vectors without shrinking the span. Okay. From this, we derive a corollary. A subset of a vector space is linearly dependent if and only if some vector Si is a linear combination of the vectors listed before it. And this is a similar proof to the other one. We just keep on throwing out vectors until we can't throw out any anymore. Well, let's just show the work here. Or actually, we can do it the other way. We'll start with the empty set, then add vectors one by one. Eventually, you'll get to a place where this set must be linearly dependent, because by the time you add all n vectors, it's linearly dependent. Okay. So we'll just choose the set of vectors not including this last one that makes it linearly dependent, and we get linear independence. Okay. So linear independence in subset. Any subset of a linearly independent set is also linearly independent. Okay, why is that true? Because if I can't find a linear combination, if I can't find a linear relation between vectors in a larger set, I certainly can't find a linear relation between vectors in a smaller set. So that means linear independence of a larger set implies linear independence of a smaller set. Similarly, if I have a linear dependent set, that means there is a linear relationship between the vectors in that set. So if I add anything to that set, it's still linearly dependent. All right, so this table summarizes the relationship. Okay, an example of lower left is the set S of all vectors in the space R2 are linearly dependent, but the subset S consisting only of the unit vector on the x-axis is independent. Okay, so you can think of examples of all of these possibilities. And that's the end of the video.